stack in order to denote the first element of the stack. Then we come to state Q2. In Q2, we can either get input A or input B. Now if we get input A, what happens? We don't pop anything from the stack, but we push that A to the stack. And by pushing, I mean inserting. So if we get input A, we just push it or insert it to the stack and we don't pop anything. And in the same way, if you get an input B, then what we do? We just don't pop anything from the stack, but we just push that B directly into the stack. That is what we do in state Q2. And then at this point, we assume that we have reached the midpoint of our string. Like for example, if we were taking this, we assume that we have completed this NO and we are reaching this middle point. So when we reach the middle point, what we do? We don't read any input symbol, we don't pop any symbol, and we don't push any symbol, but we directly go to the next state, which is state Q3. And in Q3 also, we can get inputs either A or B. And let's see what we do. If you get input A, you pop A from the stack and don't push anything. So if you get an A, you check if A is on the topmost of our stack or not. And if it is there, then you pop it and don't push anything. And similarly, if you get B, again you check if B is on the topmost of the stack, and if it is, pop it and don't push anything. So this is repeated until our string is fully consumed or till our string is finished. And after that, we assume that we have reached the end of the string or our string is finished. And when we reach the end of the string, what we do? We don't read any input symbol, but we check if Z0 is the topmost element of the stack. So if you remember, Z0 was the first element that we pushed. So when everything is popped from the stack, obviously Z0 should be the only thing remaining at the bottom of the stack, which will be the topmost element in the stack at that point. So check if Z0 is at the topmost and pop it, and then we don't push anything and we reach the final state Q4. Alright, now let us take an example to make it clear. Now let us take this example itself, A, B, B, A. A, B, B, A. Now let me draw the stack for this. So here I have drawn the stack and our input string is A, B, B, A. And we know that this is a even palindrome, because if you read it from here, it is A, B, B, A. If you read it from backwards also, it is A, B, B, A. And this should actually be accepted by this push-on automata that we have designed. So let's see if it is going to be accepted or not. So first of all, what it is, we start from the starting state Q1, and in Q1 we don't read anything, we don't pop anything, but we push this element Z0 to the stack. So let me push this Z0 to the stack. So I've inserted this Z0, and now I come to state Q2, and in Q2 I get my first input symbol, which is A. Now when I get the input symbol A, what do? I don't pop anything, but I push that A into the stack. So let me push that A into the stack. Now the next input symbol that I have is B. Now I'm still in state Q2, and when I get B in state Q2, what happens? I don't pop anything, but I have to just push that B into my stack. So let me just push this B into my stack. Now this is the condition of my stack, and if you look here, now I have reached the midpoint of my string. This is the middle of my string, and when I reach the midpoint, I told you we don't read anything, we don't pop anything, we don't push anything, but we directly go to the next state, which is state Q3. Now in Q3, let's see what is the inputs that we get. The next input we get is B over here. And in state Q3, when you get input B, what you do? You check if B is on the top of the stack and then you pop it. Now I am checking it here, and yes, I have B on top of my stack. Now I have to pop it or delete it. Now I have popped it from my stack, or I have deleted it from my stack. Now what is the next input I get? It is A. Now I am still in state Q3, and in state Q3, if I get A, what happens? I should check if A is on top of the stack, and then I have to pop it, and we don't have to push anything. Now let me check. Do I have an A on top of my stack? Yes, I do. So I have to pop this A. Now I have popped this A from my stack, and the final element that I have is Z0. And here I have reached the end of my string. I don't have anything remaining. Now when we reach the end of the string, what do? We don't read anything, but we check if Z0 is the final element or the topmost element in the stack. Let's check that. Yes, Z0 is the topmost element, and we can just pop that Z0 and we don't have to push anything. So now I have popped that Z0 from our stack, and now my stack is empty, and also we have reached the final state. So since we have reached the final state and also since our stack is empty, this string is accepted. It is an even palindrome and it is accepted. Now let me take another example. Now let's take the string A B A B. Now this string, it is not an even palindrome. Why? Because if I read it from the front, it is A B A B, and when I read it from backwards, it is B A B A. It is not the same forward and backward. So this actually should not be accepted by the PDA that we designed. So let us form the stack for this and see if this string will be accepted or not. So here I have the stack for this, and then let us come to our starting state Q1. And what do we do in Q1? We just push the element Z0 to our stack. So let me push Z0 to the stack, and then the first input that we get is A. So we are in state Q2, and when we get A, what do? We don't pop anything, but we just push the A to the stack. We push A to the stack, and then we get the next input, which is B. I'm still in state Q2, and when I get input B, I don't pop anything, but I have to push that B to the stack. So I have pushed the B to the stack. Alright, so now here I have reached the midpoint of my string again. This is the midpoint of my string. So when we reach the midpoint, what do? We don't read anything, we don't pop anything, we don't push anything, but we directly go to the next state, which is Q3. Now in Q3, let's see what we are getting. The next input that we are getting is A. So if you get A as an input symbol in Q3, you have to check if the topmost element of the stack is A, and then you have to pop it. Now I'm getting my input A, but when I check whether A is the topmost element of my stack, no, it is not. The topmost element of my stack is B. It is not A. So this state cannot proceed, and there is nowhere this state can go, and hence it cannot reach the final state. So this string will not be accepted. So this is how you design a pushdown automata that accepts even palindromes of this form. Now and there is almost check. Now we pop anything, we don't push anything, but we directly go to the next state, which is Q3. Now in Q3, let's see what we are getting. The next input that we are getting is A. So if you get A as an input symbol in Q3, you have to check if the topmost element of the stack is A, and then you have to pop it. Now I'm getting my input A, but when I check whether A is the topmost element of my stack, no, it is not. The topmost element of my stack is B. It is not A. So this state cannot proceed, and there is nowhere this state can go, and hence it cannot reach the final state. So this string will not be accepted. So this is how you design a pushdown automata that accepts even palindromes of this form. Now if you have been listening carefully, there must be some doubts that you must be having. The first doubt that you must be having is that I told you that when you reach the midpoint, we don't read anything, we don't pop anything, but we go to the next state. So in the first half, we just push the elements to the stack, and then when we reached the midpoint, we started popping the elements. But how do we really know when we have reached the midpoint of our stack? There is nothing here to specify that I have reached the midpoint of the stack. So how do we know that I have reached the midpoint of the stack or not? And how do I know when should I take this transition from state Q2 to Q3? This is one question you must be having. So this question I will be answering in the next lecture, and I will be explaining it in a very detailed way. But in the meanwhile, in the last lecture, we have seen an example of pushdown automata where we design a pushdown automata that accepts even palindromes over the symbols A and B. And we have also taken some examples, and we have seen how the pushdown automata actually works. And if you have not watched that lecture, I request you to watch it first before you proceed with this one. So basically how the pushdown automata works is that in the first state, which is our initial state Q1, we just push a symbol Z0 into our stack in order to denote the bottommost symbol of our stack. And then in the state Q2, we read the first half of our string and then we just push it onto the stack. And then when we reach the midpoint of our string, state Q2 goes to state Q3. And then in state Q3, what we do is we read the next half of the string and we compare it with the elements of our stack and see if the elements that we get are same as the elements on top of the stack, and we just pop them. And finally, when we reach the end of the string, we check if Z0 is the bottommost element, and if it is, we pop it and we reach the final state. So that is how it checks whether this is an even palindrome. But there was a question that we had, and what was the question? The question was that how do we know that we have reached the midpoint of our string so that we can go from state Q2 to state Q3? We don't know how or when do we reach the midpoint of our string. So we said that when we encounter an epsilon, we understand that it is the midpoint of our string and we go to state Q3. So let me assume that there is an epsilon over here which is at the midpoint of this string. But how can we just assume that the epsilon is only over here? As a human being, I know it because I can just look and say that this is the middle of the string. But the system that we have designed here, how does it know that this is the midpoint and the epsilon will be present here in order to separate the first half and the second half? So the answer is that it doesn't know that the epsilon that separates it is over here. So what we will assume is that we will let the machine or the push-on automata assume that there are epsilons everywhere. On every sides of every symbols there is an epsilon. So in this way we assume that there is epsilon present after and before every symbol set we have. So this is a much easier assumption to make, and let's see how does the machine or the push-on automata that we have designed works when we assume that there is epsilon on every sides of every symbols. So let's see how it works. So here I have drawn the diagram of our stack in order to explain to you how this actually works. So don't be afraid seeing this diagram. I will explain to you step by step and we will understand and we will be clear how this works when we complete this lecture. So let's keep in mind that the string that we are going to check for is A, B, B, A. And this is an even palindrome because whether you read it from forward or backward, it is still A, B, B, A. Even from backward it is A, B, B, A. So according to the push-on automata that we have designed, this string should be accepted. Alright, so let's take these inputs and see what happens. So the first input that we have is an epsilon. Now in Q1, if we get epsilon, what happens? We don't pop anything, but we just push the symbol Z0 into our stack. So this is what I have shown. In state Q1, when you get epsilon, it just goes to state Q2, this one Q2, and then this is our stack, and we push the symbol Z0 to our stack. And why do we do this? We do this in order to know that what is the bottommost symbol of our stack. Okay, now the next input that we get is A. Now when we get A, what happens in state Q2? In state Q2, if you get the input A, what we do is we don't pop anything, but we just push that A into the stack. So we are still in state Q2, and the A that we get, this A, we just push it into the stack and we don't do anything else. And now after we reach this A, here there is an epsilon and here there is a B. Now I told you our machine doesn't know that whether it should be an epsilon that should be read here or whether it should be a B. So we will consider both cases. We will first read an epsilon and see what happens, and we will also see if we read a B, what happens. So first let's see that if we read an epsilon, what will happen. So we are still in state Q2, and in state Q2, if you get epsilon, what happens? You should not push or pop anything from the stack, but just go to state Q3. So that is what I have shown here. If you get an epsilon, or if you read an epsilon here from this state Q2, if you read epsilon, we don't push or pop anything from our stack. The stack remains exactly the same, but we go to the next state, which is state Q3. Alright, now let us proceed in this direction and see what happens. Now we are in state Q3, and then the next input that we get is B. Now even here there are two options. We can either read B or we can either read epsilon. Now if we read B, let's see what happens. In state Q3, if you read a B, then what you should do is you have to check if B is the topmost element of the stack. So let's see, if we are going to read a B, we see that B is not the topmost element of our stack. The topmost element of our stack is A. So we see that this route cannot proceed anymore. This is wrong. Now I said we can also read epsilon. We could also assume that instead of B, it is epsilon over here. Now in state Q3, if you read epsilon, what happens? In state Q3, if you get an epsilon, then we have to check if Z0 is the topmost element of the stack, and if it is, then we can go to the final state. So let us see. If you read an epsilon in state Q3, we have to check if Z0 is on topmost of the stack. But this is the stack we have, and the topmost element of our stack is A, and it is not Z0. So this route or this branch is also wrong, and we cannot proceed in this way. So these two cases have failed. Alright, now we have to come from where we started. We came this way. Now there was another option, that is this route. And what is that route? We already read epsilon and A, and instead of taking B, we took epsilon and saw what happens. We saw that this route fails. There is no path to follow. So we know that taking this epsilon is not correct. So we have to take a B instead. Now if we take B in this state Q2, let's see what happens. In our state Q2, if you get input B, we don't pop anything, but we just push B into the stack and we still stay in state Q2. And that is what I have shown here. In state Q2, if you get B, which is this B, we don't pop anything, but we just push or insert this B on the top of the stack. This was my stack, and I have inserted B on top of the stack, and we still stay in state Q2. Alright, so we have completed up to here. Now the next symbol that we can read is epsilon, or we can also ignore this epsilon and read B. There are two cases. So first let us read this epsilon and see what happens. So if you read epsilon in state Q2, what happens? In state Q2, if you read epsilon, you have to go to state Q3 without pushing or popping anything from the stack. So that is what I have shown here. If you read epsilon in state Q2, then we just go to state Q3 without changing anything in our stack. This was my stack. I read epsilon. My stack remains the same, but we just go to state Q3. So we are over here right now. And let's see, if we proceed in this way, where do we reach? So what is the input symbol that we read? We read epsilon. And now the next symbol that we have is B. Now here also we can either read a B or we can either read epsilon. So first let us read B and see what happens. So we are in state Q3, and in state Q3, if you read B, you have to check if B is the topmost element of the stack, and if it is, then you have to pop it. Now we are here, and then we read a B, and if we read a B in state Q3, you have to check if B is the topmost element of the stack. And when I check it, I find that yes, B is indeed the topmost element of my stack. So I have to pop that B, and I still stay in state Q3. So this B which was there is popped or removed from the stack, and this is the condition of my stack right now. Now since this direction is proceeding in a good way, let us continue in this direction and see what happens. Okay, so we just read this B and we are not considering this epsilon right now. So the next input that we can get is either A or epsilon. Now let us see, if we get A, what happens. In state Q3, if I get A, then I have to check if A is the topmost element of my stack, and if it is, I have to pop it and still stay in state Q3. So we were over here right now, and we considered that we are reading the input A. Now if you read the input A, what happens? You have to check if A is the topmost element of the stack, and when I check it, I find that yes, A is the topmost element of my stack. So what I have to do, I have to pop that A and still stay in state Q3. So I have popped that A from my stack, or I have removed that A, and I still stay in state Q3. Alright, so we are here right now and it is proceeding in the correct manner. So let us continue in this way and see what happens. Now we have read this A, and then what we have is epsilon. We have reached the end of the string actually. So there is an epsilon over here, and we are in state Q3. In state Q3, if we get epsilon, what happens? we have to check if Z0 is on top of the stack, and if it is, you can pop that Z0 and go to the final state Q4. So let's see what happens. We were over here, and what we read was an epsilon because we have reached the end of the string, and we have to check whether Z0 is the topmost element of the stack. And yes, Z0 is the topmost and the only symbol in my stack now. So I can pop it. So I have popped it, and we have come to the final state, which is Q4. Q4 is the final state, and my stack is empty. So if you follow this path, you see that we have reached the final state, and also our string was accepted. So that path is the path that you have to follow in order to accept the string ABBA. Now there are also other routes that we have to see and check whether those routes lead to final state or not. So let us check all the routes and see where do they lead. Now here, this was the path we took and we reached the final state. Now here is one path that we did not discuss. Now here, instead of reading an A at state Q3, if we read epsilon, then what would have happened? What I am talking about is this one. Here, after we reached this epsilon, we read A and it was correct. But instead of reading this A, if we read epsilon, then what would have happened? In state Q3,
I'm zoned out now. I'm pretty zoned out right now. Like, I
automata.
don't know
In this
what's
lecture
going on.
series, we have been studying about one. So if you remember, in the very first lecture of this lecture series, this was the diagram we had where we discussed what were the topics that we are going to cover in this lecture series. And if you see, we have already studied about finite state machines and push-down automata. And in finite state machines, we have seen that the class of languages accepted by them is known as the regular languages. And then in push-down automata, the class of languages that was accepted by them was the context-free languages. So we saw the limitations of finite state machines, and we saw how its limitations were overcome by push-down automata because it is more powerful than finite state machines. And now as we move one step ahead, we are going to study about Turing machine, which is more powerful than finite state machines and also more powerful than the push-down automata. And the class of languages that is accepted by the Turing machines is known as recursively enumerable languages, which we will be discussing in detail as we proceed further in this module of Turing machine. Now let us see what were the data structures that we had in finite state machines and push-down automata, and let's see what is the kind of data structure that we will have in Turing machines. So if you remember, in case of our finite state machines, which accepted the regular languages, the data structure that we had was only the input string. We just had an input string and we had a control which can move only to one direction, and that is forward. So we saw the finite state machines and we saw that they had a very limited power and also a very limited memory. And the class of languages accepted by finite state machines are the regular languages, and we already saw what are those regular languages. And coming to push-down automata, in push-down automata, the data structure that we had was the input string, and apart from the input string, we had a stack. So what made the push-down automata different from finite state machine was the presence of a stack. So because of the presence of this stack, we saw that the push-down automata was more powerful than finite state machines, and then the class of languages that they accept, which is known as the context-free languages, are a higher class of languages as compared to regular languages. So this is the diagram which represents that. We had the input string and also the stack, which added more power to the push-down automata, making it different from the finite state machines. Now coming down, we have the Turing machines, which we are going to discuss in this lecture. And in Turing machine, the data structure that we have is something known as a tape. So a tape is something that looks like this as it is shown in this diagram. So we see that the tape is a sequence of infinite symbols. It is an infinite sequence, and over here we have something known as a tape head. So the tape head is positioned on the symbol on which the current control is present, and then the tape head, it can either move one step to the left or one step to the right depending on the kind of computation that we have. And then here we have the input symbols, and as I told you, this is an infinite sequence. So the input symbols that we have, they are filled into these cells, and then the remaining cells, instead of leaving them just blank, we fill them with a special kind of symbol that is known as the blank symbol. And if you see here, we have the tape alphabets, which is represented by sigma. You know, sigma is used to represent the input symbols. We have been studying this from the beginning of this lecture series. And the tape alphabets, it is used to represent the input symbols. We have been studying this from the beginning of this lecture series. And the tape alphabets, it can contain 0, 1, A, B, or any kind of symbols like this. And then, as I told you, the blank symbol is a special symbol. And something you need to note is that the blank symbol, it does not belong to sigma. That means the blank symbol is not a part of the tape alphabets, or it is not a part of the input symbol. But what is it? It is just a special symbol that is used to fill the infinite tape. So, as we are having an infinite tape, the blank or the empty cells are filled with this special symbol known as the blank symbol, represented by this. So this is the basic data structure that we have in our Turing machine. So the main thing that you need to remember is that the tape is an infinite sequence, and then the tape head is the position where the current control is present, and then the empty cells are filled in by a special symbol known as the blank symbol. Now let us look at the initial configuration of a Turing machine. So if we have a Turing machine, the initial configuration of the tape, it looks something like this. So here, as I told you, we have the input strings represented by these symbols over here, and then the empty cells, it is filled by these symbols known as the blank symbols. So it blanks out to infinity. And then we have the tape head, which is positioned on the leftmost end at the starting. And now let us see what are the operations that we can have on the tape. So these are the operations that we can have on our tape. So the first one is read or scan symbol below the tape head. So as I told you, this tape head represents the position at which our current control is present. So you can always either read or write only that symbol which is present exactly below the tape head. So if you are having your tape head over here, you can read or scan the symbol which is exactly below the tape head. And then the second operation that you can perform is update or write a symbol below the tape head. So again, we have to see where is our tape head, and then the symbol below the tape head can be updated. That means, for example, we have A over here. This A can be updated. That means it can be overwritten by some other symbol, let's say B. So we can replace this A with B or anything else depending on the input symbols that we have. So you can either read the symbol below the tape head, or you can write a symbol below the tape head. And then the other operation that you can perform is move the tape head one step left and move the tape head one step right. So you can either move the tape head one step to the left or one step to the right. So remember that you cannot move more than one steps, but only one step you can move either to the left or to the right. Machine of operation machines. Now coming down, we have the Turing machines, which we are going to discuss in this lecture. And in Turing machine, the data structure that we have is something known as a tape. So a tape is something that looks like this, as it is shown in this diagram. So we see that the tape is a sequence of infinite symbols. It is an infinite sequence .
It's time for a break now. 30 minutes are up. 10-minute break.